Okay, let's run down a quick review for your second midterm. And on my left side here is a review of the sheet, or it's the sheet that you guys should have been able to download. And we'll try to put the solutions on the right side. All right, for the first one, part A. For the method of undetermined coefficients, the assumed form for a particular solution yp for this differential equation is going to be given by what? So, well, for this, we don't care too much about the left-hand side, and we're focused more on the right-hand side, the non-homogeneous part. And so, looks like we have a polynomial here, 1. It's really just a constant, so we'll represent that as a constant. So then our y sub p function is going to be a constant. And then we have an e to the x power. And so what we're going to do is we're just going to tack on another constant in front of that. So plus another constant times e to the x power. And so that should be our y particular. And what we would do is take a couple of derivatives and then put it back into the differential equation and then solve for a and b. And then we would have our solution. All right? Let's take a look at part B. If y is equal to e to the negative x over 2 times cosine root 3 over 2x is a solution to a second order linear differential equation with constant coefficients, then the general solution is going to be given by what? So our first solution is, let's call this answer our first solution, y1. And remember that for a second order differential equation, we have two linearly independent functions and then a linear combination of that will be our solution. So let's express this as a linear combination with c1 and then e raised to the minus x over 2 times the cosine of, and that's the square root of 3 over 2 whoops, let's get this formatting correct. Okay, square root of 3 over 2 times x. So this is one solution, and according to our superposition principle, we will be tacking on another c2 times the kind of like the partner function of this thing. And so our partner function with the cosine is going to be the sine. If you remember where this came from, we're assuming that the solution to our auxiliary equation is going to be negative 1/2 plus or minus square root of 3 over 2i, and that's how we were able to get this combination of e's, exponentials, and the sine and cosine functions. All right. So part C, suppose that m is equal to 2 with multiplicity 2 and m, should be m2 I guess, but m2 is equal to negative 1 with multiplicity 3 are roots of an auxiliary equation. Write down general solution corresponding to the homogeneous linear differential equation with constant coefficients. Alright, so we're still dealing with constant coefficients. We're assuming that our solution is is 2 and -1, but with multiplicity. And so if you remember the constant coefficients, the solutions to constant coefficients are of the form e to the mx. So if we want the general solution, one has multiplicity 2, the other one has multiplicity 3, and so we have to assume that this is at least a fifth order differential equation, and if those are all the solutions, then it has to be exactly a fifth order differential equation. So a fifth order differential equation will have 5 arbitrary constants. So let's start building our arbitrary constants. We have C1 through C5, and we have 2, m is equal to 2, and so we will have an e raised to the 2x as a solution. Now, if this has multiplicity 2, then it has to repeat itself, but it can't repeat itself exactly as is, because then it would be linearly independent. And so there is a technique that we discussed in class where if we have a solution, we can find another solution. And so we won't go through exactly that process, but what happens to that is that we have the same e to the whatever power, and then we just tack on an x next to it. Alright? So that takes care of m is equal to 2 with multiplicity 2. And now we have another m that has multiplicity 3, and that's m is equal to -1. So we have another arbitrary constant, C3, and then we have e raised to the -1 times x. Okay, and this has multiplicity 3 this time, and so what we do is each time we account for its multiplicity, we add on another x. So this is the fourth one times x, and then that e to the -x, and then finally we have our last one. This is what makes it a fifth order differential equation, and this time instead of just x, we have to do x squared, and then we tack on that last e to the -x. Okay, so this is our general solution. Alright, the last one, what is the Wronskian of the three functions? We have e to the x cosine squared x, and e to the x cosine squared x. Well, it looks like a y2 and y3 are linearly independent, or linearly dependent, sorry. So y2 and y3 are linearly dependent, and if that's the case, the Wronskian is going to have to equal to 0. So we don't even have to do the computations. I mean, you can do the computations if you want, but you'll see that remember that if it's independent, then we get a non-zero result. If it's dependent, we get exactly 0. Okay, I think that takes care of number 1. Let's move on to number 2. Here we're actually solving for the differential equations, and we'll start off with the homogeneous differential equations. And here is our first function, our first dE. We have y double prime plus 2y prime plus 3y is equal to 0. And what we want to do is we want to come up with our auxiliary equation. So our auxiliary equation is going to be m squared plus 2m plus 3 equal to 0. And then I think if we factor this, we should get imaginary numbers. I don't think we can factor this. So it looks like we will have to use a quadratic equation, quadratic formula, and so we'll get our solutions to be m is equal to, let's set up a fraction here. So our m should be equal to minus b, so it's negative 2. We have a plus or minus a square root. Let's get the square root here. Square root of b squared, and b was equal to 2, so that's 4. Minus 4ac. We have 4 times 3 is 12. So that gets negative 9 under square root. And so we're going to have a 3i there. Divided by 2a. Okay. So we have a negative 2 over 2. So that's as good as saying negative 1. And then we have a plus or minus. And then under the square root here will be 9, and the square root of 9 is 3, and then it's negative, so it's called 3i. So we have the root 3 over 2. So square root of 3 over 2i, and that is going to be our solution, or that's going to be our solution to our auxiliary equation. And so what we're going to come up with here is a y1. Let's go ahead and jump to the general solution. Y is equal to a constant times our y1. Now our y1 is, because this has a real part, that's going to be the e part, so minus 1 times x, so that's e to negative x, and then we have the sine or cosine. Let's do cosine first. Cosine of the imaginary part, which is root 3 over 2. So that would be root 3 over 2 times x. And we will also have the corresponding matching function whenever we have a sine and cosine. Whenever we have one of those functions, we have the other function. So I think this should be our general solution. I don't see any initial conditions, so we don't have to solve for C1 and C2. If you do have initial conditions, then make sure you don't forget to solve for that other stuff. All right. Now let's take a look at the second one over here. We have our differential equation is 6x squared y double prime plus 5xy prime, and then we have a minus y is equal to 0. So this looks like it's a Cauchy-Euler equation, and so we're going to assume our solution is of the form y is equal to x raised to the m power. So instead of e raised to the x times m, our solution will look like this. We've done this several times already, so we should be used to our auxiliary equation. And if you're not, just make sure you look it up again. Our auxiliary equation would be a2, so that's 6 times m squared. 6m squared. And then we're adding, now this is the a1 minus a2, so that's 5 minus 6 times m, and then we have a minus 1, that's our a sub 0, and then that's equal to 0. So when we're looking at this, we can simplify this a little bit and see how we can solve for this. And it looks like the only thing to do is to simplify the m term, and it looks like we can get that down to minus 1. Whoops. So let's say minus 1 times m, and then there's a minus 1 here. So I think you can factor this, but just to be sure, let's again use a quadratic equation. So our quadratic equation says that our m is going to equal to, and let's get this set up in a fraction. And we have negative b, so let's just call that a plus 1. B is equal to negative 1, so that's plus 1. Plus and minus, and then we have the square root of b squared, so that's going to be a 1 minus 4a, a is 6, and c is negative 1, so that becomes a positive. So 4 times 6 is 24. And then times negative 1 is positive 24. So that gives us a square root of 25, which is 5. And then we have 2 times a, which is 12. And so what does this turn out to be? We have a 1/12 plus or minus, and then we have 5/12. Okay, so it looks like this is either going to be m is equal to, if we do the addition first, that's 6/12, so that's 1/2, or our other solution would be that's 1 minus 5, so that's negative 4/12. So that becomes negative 1/3, I believe. So here are our two solutions, and these will end up being powers of x, remember. Okay. So let's put that together. And so our solution is going to be y is equal to c sub 1 times x. Remember that these are x powers raised to the 1 half, and then we have plus c sub 2 at times x raised to the negative 1 third. And I think that should be it. Alright, so that's number 2. Alright, let's move on to number 3. And for this problem, we are using undetermined coefficients to solve for this. So let's start off by writing our differential equation. Y double prime plus y prime plus 3y is equal to 0. So, like always, we start off with our auxiliary equation, m squared plus m plus 3 is equal to 0. Not a nice way to factor, so let's go ahead and use our quadratic formula. M is equal to what is m going to equal to? So negative b, so that's negative 1 plus or minus the square root. And we're looking at the square root of b squared, so inside here is 1 squared minus 4ac, so that's 4 times 1 times 3, so that's 12. All divided by 2a. So we got square root of 11i, looks like. So let's see if we can just write this as negative 1 half plus and minus, and then the square root of 11. So I'm just going to copy this and make this into an 11 divided by 2. Alright, so it looks like that's going to be our solution to our homogeneous or the auxiliary equation. And so the solution should look like this. Y is going to equal to, let's call it y sub c, and this is equal to c1 times e raised to the negative 1 half x, or let's just call it negative x over 2 times cosine of, and then this will have a square root of 11 over 2 times x, and then we'll have the exact same thing except with a sign. So just copy and paste that and change a couple of things here, like the sub 1 and the sub 2, and then the sign, the cosine into sine. Okay, so that's the first part of this. And now we need to find out our particular solution. Um, and based on our right hand side is 2x. Our particular solution should look like a linear term. So y sub p, our particular solution, should equal to um, a linear term. So instead of just ax, because it's 2x that we're looking at here, instead of just ax, we need to consider the actual linear term. So a linear term is ax plus b. Now, based on that, we need to make sure we find the first and second derivatives, put it back into the original equation, into the original differential equation, and solve for it. So the derivative of that is a, and then the second derivative turns out to be 0. Y sub p prime, double prime, is going to equal to 0. Alright, so we'll put it into our differential equation. Remember though, our differential equation is non-homogeneous, so the differential equation should have a 2x here. That's the original problem with a 2x. And so we're going to plug in what we have for the derivatives. And so for y double prime, we got 0. So let's put 0 in. For y prime, we have a. And for y, we have a x plus b. Okay, so that is going to be set equal to 2y. Again, I'm going to pick this whole thing up and copy it. And, well, I could just copy this part. Whoops. So I have a, and then this is going to be 3ax and 3b. And so what we're going to do is we're going to gather the like terms so that we can set some of these equations equal to each other. So what are the like terms we're going to gather? It looks like it's going to be 3a with the x and a plus 3b for the constant term. So if we just move things around and then match this up so that the 3a is going to equal to 2. So 3a, let's do this in an equation. 3a equal 2, and that means, what does that mean? That means a is going to be equal to 2/3. And then we have a plus 3b, and that's going to equal the constant term, which is 0. But we know that a is equal to 2/3. So let's replace a with 2/3. And then we can solve for b. So 2/3 goes on the other side as negative, and then we'll divide by 3. So it looks like b is going to equal to negative 2/9. So that should be our solutions, and we just need to string them up. Um, Again, the y sub p is equal to this business over here. And then we found that a was equal to 2/3. And we found that b was equal to minus 2/9. And that's our particular solution. So now that we have a particular solution, the general solution is going to be y equals our first solution from the homogeneous differential equation, and then tack on our y sub p from our particular solution. And that's it. So if we had initial conditions, we probably would have solved for the initial conditions before we solved for y sub p. So I think this is good. Let's take a look at part B now. This time we are using variation of parameters. So let's see how this is going to fly for us. So 3b, we have our differential equation is y double prime plus y is equal to cosine squared of x. Alright, so what do we need for the variation of parameters? Well, it looks like first we will need the solution to our homogeneous part. So the auxiliary equation is going to be m squared plus 1 equals 0, and that's going to give us plus and minus I. So let me skip a couple of steps here. And then get that our solution is going to equal to C1 cosine x plus C2 sine x, and then this gives us our fundamental solutions, cosine and sine. So variation of parameters, we need the Wronskian, so we'll need a W is equal to so we need the determinant of a 2 by 2 matrix. So our 2 by 2 matrix is going to be the sine and the cosine. I put my cosine first, and so I'll have that first. My sine is in my next function slot, and then now down here the derivative of cosine is negative sine, and then the derivative of sine is positive cosine. And so the determinant of this, we've seen this enough times, we can just say that this is sine squared and cosine squared. So the Wronskian is 1, it makes it nice and easy for us. Now we need a couple of other Wronskians that are slightly modified. So what I'm going to do is just, it's exactly this, except we change the first column for the first. Alright, so we're filling out this Wronskian. Our coefficient here is 1, so we are already in standard form, so our function is really just going to be that cosine squared x. And what I want to do is I want to change the first column here to be 0 and cosine squared x. So this is what I have, and I want to find the determinant of this, and the determinant going diagonal is 0, and then we have a minus sign, and then we have a cosine squared x times sine x. Okay? So with the Wronskian, the original Wronskian is 1, this is going to make life a little bit easier for us when we need to find out what u sub 1 is. So we know that u sub 1 prime is going to equal to exactly this business over here. Divided by 1, because that's our Wronskian. So I think I would just do a u substitution, let u equal a cosine x, and du is going to be negative sine x, so that's going to cancel a negative sign. I'm doing this so I can find out what u is actually equal to. So the antiderivative after u substitution is going to be cosine, or u squared. Antiderivative u squared is u cubed over 3. So let's write that as a 1/3 u cubed, but u is equal to cosine, so let's say cosine cubed of x. Okay, so that's our first function. And then we want to tack on the cosine for that. This is u1, y1 business. And so our y1 is the cosine function, and so this is our u1. Alright, we'll put that together later. Let's, for now, work on the second Wronskian, or I guess it would be considered the third Wronskian. That would be w sub 2. Oops. So w sub 2, and we will be changing the second column this time. So the first column stays the same, the second column changes to 0 and cosine squared. And so the determinant of that looks like it's going to be cosine cubed minus 0, so it's just cosine cubed. So the antiderivative of that, well, before we jump to the antiderivative, let's write out our u sub 2 prime, and that would be cosine cubed. And just to get us ready to integrate this, because that's what we're going to do, let me just write it as cosine squared, or 1 minus sine squared of x times cosine x. So that's the technique for integrating this. We're going to let u equal to sine, and then take the antiderivative with respect to u, and then get our solution. So let's see how this is going to go. it looks like our antiderivative is going to be, so the first one is going to be u, and the u is equal to sine x. And then the second one is u squared, and then I take the antiderivative of that, that's going to be u cubed over 3. So let's start off with a 1/3, and then u is equal to sine x, and the sine is going to be raised to the 3rd power. Whoops, to the 3rd power. Okay. Oops, I want to say finally, we want our general solution. Our general solution should look like this. Y is going to equal to YC, which we found already, and then we want to add on YP, and remember that YP is actually equal to U1 times Y1 plus U2 times Y2. Okay, so all the pieces are here, so let's write out our final answer. Y is equal to the YC business that we got earlier, plus, start with U1. U1 is this thing, and then Y1 was the cosine of x, and then plus U2 is this thing, and since this has multiple terms, I better put parentheses around just in case. Let's not lose anything here. And then we're going to multiply that times U2, which is sine x. So, yeah, I think that should be it. I was going to see if there's anything that might cancel if we work things out, but it looks like it's fine. So this is going to be our final answer for number 3B.